In the first example, we need to divide a Class A network 50.0.0.0 into 2 equal networks. We're going to need 2 identical networks, and then we're going to have to determine network address for each of those networks, first usable address, last usable address, and a broadcast address for both of those networks. Then we're going to look at the binary format of each of these addresses, and then we're going to transfer that into the decimal format. First, let's calculate the binary value of our Class A IP address. The first bit, which has a value of 128, is going to be switched off because we don't need it. The second bit is 64, and we don't need that either. The third bit from left to the right is going to be 32, and we're going to need that. So that bit is going to be turned on. The next one is 16. 32 plus 16 is 48, so we need that too. The next one is 8, and if we added that to 48, that would be 56. That's too much. The next one is 4, which is also too much if we add that to 48. And the next one is 2. We're going to need that. 48 plus 2 equals 50. And then the last bit is 1. Obviously, we're not going to need that one. And we've got ourselves our first segment or our first octet of our IP address. The next 3 octets are going to be all zeros, so that's easy. The first 8 bits in this IP address are going to be the network portion. And we know that because all Class A networks are /8 networks. Now, in order to divide this network, we're going to use the first bit after the network portion. We're going to take this bit and join it into the network portion, into the existing 8 bits. So now we're going to have 9 bits representing the network portion. Now, even though this 9th bit is the part of the network portion now, or it's part of the new network portion for the new 2 subnets, it's still going to be 0. So our network address for our first subnet is going to be 50.0.0.0. Our first usable address is going to be the same as this, but we're going to switch the last bit to 1. So we're going to copy all the previous bits, and then we're just going to use 1 at the end. There it is. So the decimal representation of that address is 50.0.0.1. Now our last usable address is going to be the opposite of that. So we're going to take our first 9 bits, which represent the network portion, and we're not going to change that, but we are going to change the remaining bits to 1s, except for the last bit. If we use 1 in our last bit also, that gives us our broadcast IP address. So the last usable IP address is actually going to be the broadcast address minus 1. So this is what that will look like. We copy the network portion, which are the first 9 bits, and then we use all 1s, but the last bit is still going to be 0. And in decimal numbers, that's going to be 50.127.255.254. The broadcast address is going to be, as I mentioned earlier, literally just the next IP address after the last usable IP address. And in decimal numbers, that's going to be 50.127.255.255. For our second subnet, we're going to have to switch our 9th bit from 0 to 1. Actually, this bit could be called the subnet portion. So in this example, we actually have 3 portions. We have the network portion, the subnet portion, and the host portion. So this subnet bit is 0 for the first network and is going to be 1 for the second network. That's going to be, if this is 1, our network address is going to be the first 8 bits, or the first octet is still going to be the same, but then the 9th bit is going to be 1. And then the rest of the bits for the network IP address are going to be zeros. And in decimal format or in decimal numbers, that's 50.128.0.0. To determine our first usable address, we're going to copy the network portion, and then we're going to use all zeros, but for the last bit. For the last bit, we're going to use 1. And in decimal numbers, that's 50.128.0.1. The last usable IP address is just going to be the opposite. So instead of using all zeros after the network portion, we're going to use ones, except for the last bit. The last bit is going to be 0. And in decimal numbers, that's 50.255.255.254. The broadcast IP address is just going to be the next IP address, which is 50.255.255.255. Welcome to subnetting a Class A network using FLSM, example number 2. This time, we need to subnet a Class A network, 21000, and the question is, how many Class C networks can we create? Right now, we have a network 21000, where only the first octet represents the network portion. We need to create Class C networks, which means that the first 3 octets will represent the network portion. So the first network here is going to be /8, and that's a Class A network. And the second network is /24, and that's actually a Class C network. Our task here is actually pretty simple. We only need to calculate the number of combinations we can get from these 2 octets in the middle. So in a Class A network, the first octet is going to be the network portion, and we can't change that because that's defined in the requirement. We get a Class A network 21000, and the network portion you can never change. So the only part we can change are these 2 octets in the middle, and that's 2 to the power of 16. So that is our answer. That is the number of Class C networks we can create out of any Class A network. I'm actually going to try and prove that to you. So we're going to look at the binary representation of our network 21000, and we're not going to change the first octet and the last octet. So the first octet we're not going to change because we can't change it. That's what we got in the requirement. So that's our Class A network, and the network portion we can't change. For example, if we're a company or, I don't know, an internet service provider or anything like that, and we buy this network. So we are assigned 21000, and we can change the host portion, the original host portion, but we can't change the original network portion. So we're going to use the middle 2 octets as a subnet portion. The first octet is going to be the network portion. The second and the third octet are going to be our subnet portion for our C networks. And then in all of our C networks, the last octet is going to be the host portion. So of course, we're going to be changing the host portion to assign specific IP addresses to specific endpoints or hosts or whatever. But for subnetting purposes, we're not going to change that last octet. So for example, the first class C subnet is going to be 21000. The second one is going to be 21010. The third one is going to be 21020, etc. It's going to be 2, 3, 4, and then we're going to go all the way to 255 in the third octet. Once we've filled the third octet for the first time, we start changing the second octet. So now the second octet is going to be 1. It's going to be 21100. And then we start filling out the third octet all over again from 1 to 255. Once we've reached 255 for the second time in the third octet, we're going to start increasing the second octet. It's going to go to 2, 3, etc., etc. Our last class C subnet in this example is going to be 21255 0. So we're going to go all the way from 21000 to 255 0. So hopefully you got the point. We start changing the third octet first, and then once we've filled out the third octet for the first time, we change only 1 bit in the second octet. And then we start filling out the third octet all over again. And then when we fill it up again, we change 1 more time the second octet. And we continue to do that until we get all ones in binary value, of course, in the second and third octet. All right, this time we're asked the same question as in the previous example, only here we have a class B network. So how many class C networks we can create out of a single class B network 155.3.0.0? So in a class B network, our subnet mask is /16, which means that the first 2 octets represent the network portion. In a class C network, the first 3 octets represent the network portion. So the difference in this example is only 1 octet. And our answer is pretty obvious here. It's 2 to the power of 8. If we try and do the same thing we did in the previous example and go from the first subnet to the last subnet, it's going to look something like this. So the third octet, or our subnet portion, is going to go from 0 to 1, 2, 3, 4, etc. And then when it's up to all ones, that's 255. And that is our last C network or C subnet in this example. Subnetting a class B network using FLSM, example number 2. This time, we've been allocated a class B network address of 189.2.0.0. And we need to create at least 9 subnets with 64 addresses, and then 5 subnets with 100 addresses, and then 13 subnets with 70 addresses. Now, to clear this up, we're not looking to create 9 subnets with a total of 64 addresses, but 9 subnets with 64 addresses for each of those 9 subnets. So for example, for these 5 subnets with 100 addresses per subnet, it's going to be a total of 500 addresses for all of those 5 subnets. The way we do this is, first, we need to find a common subnet mask that satisfies all requested subnets. And then we need to count the number of subnets needed. So for our first task, we're going to look at the largest subnet, and that's obviously the 100 addresses subnet. If we satisfy the largest subnet, we're going to satisfy the smaller subnets. So we need to figure out how many bits we need to use for our host portion to be able to create at least 100 different addresses. That's going to be 7 bits because 2 to the power of 7 is 128. If we used 6 bits, that would be 64 different addresses. And that's actually enough for these 9 subnets, which require 64 addresses each, but it wouldn't be enough for the other 2 types of subnets. If we use the 7 bits for the host portion, we are left with 25 bits for the network portion. But we got a Class B network, which means that the first 16 bits are never going to change. So that's our default network portion. The bits that are left in between our network portion and our host portion is going to be our subnet portion. That brings us to our second task, which is count the number of subnets needed. So we need 9 subnets, and then 5 subnets, and then 13 subnets. In total, that's 27 subnets. Now we just need to make sure that we can fit the 27 subnets into our subnets portion. And this portion has 9 bits, which means that we could actually create 512 of these subnets. So our answer to this requirement is if we use 189.200/25, we could create all of these subnets. That's pretty simple, so let's look at an extra question. Let's name the first, the 11th, and the last subnet. The first one is obvious. It's going to be 189.200. 11th is a bit trickier. Let's go from the first. So this is the first, where we have all zeros in the subnets portion. And this is second, and then this is third. But we can't keep on going like this. What if you get asked, what's the 100th subnet out of 1,000? So we need to automate this. Let's look at it this way. If our third subnet has a value of 2, but we're looking at these 9 bits as if there is no dot. So if our third subnet has a value of 2, then our 11th subnet will have a value of 10. And this is going to be the value of 10 if we use 9 bits to write it in binary format. So this is our 11th subnet. If we wrote this in decimal format, this one has a value of 1 in this one octet. In this third octet, this is 1, and then this is 2 that switched off, and then this is 4. So our 11th subnet is going to be 189.2.5 in the third octet, and then 0 in our fourth octet. And this is, of course, /25. Finally, for our last subnet, so we said that in total we have 27 subnets, so we're looking at the 27 subnet here. So the 27 subnet is going to be 26 in binary format in our subnets portion. If we look at these 9 bits, this 0 is 1, and then this 1 is 2, and then this 0 is 4, and then this 1 is 8, and then this 1 is 16. When we all add all of those up, that's going to be 26. But then when we look at this octet, these are different values. So this is 1, and then this is 4, and then this is 8. In total, that's 13. So our 27th subnet is going to be 189.2.13.0. And of course, that's going to be with /25. This time, we're going to use FLSM to subnet Class C networks. We're going to go through several simple examples. In the first example, we need to answer how many subnets can we fit into a Class C network if each subnet has at least 10 addresses. Let's think about this for a second. If we need 10 addresses per subnet, we need to figure out how many bits we're going to use for our host portion. In order to create at least 10 addresses per subnet, we're going to need 4 bits for our host portion. 2 to the power of 4 is 16. If we used 3 bits, that wouldn't be enough because 2 to the power of 3 is 8. So we're going to use 4 bits for our host portion. That means we're left with 4 bits for our subnets portion. Since we started with a Class C network, which is /24, which means that 24 bits are going to be used for the network portion, and we've decided to go with 4 bits for our host portion, we're left with 4 bits for our subnetting portion. So in our subnetting portion, we can create 16 different combinations or 16 different subnets. Let's look at an example. Let's say we started with 10, 10, 10, 0, /24, of course. So in binary format, that would look like this. If the first 24 bits are the network portion, and we use the last 4 bits for our host portion, we're left with 4 bits for the subnetting portion. In total, that's 16 different subnets with 16 addresses per subnet. Now we're going to take this answer and these 16 subnets that we have right here, and we're going to look at some further questions. Question number 1. Is address 10.10.10.72 in the same subnet as 10.10.10.80? Let's look at what these 16 subnets look like. So the mask for all of those subnets is /28. A short reminder here. We started with /24 because we had a Class C network in the beginning. And then we decided to use 4 bits for our host portion and 4 bits for our subnetting portion. So the subnetting portion becomes a part of the network portion. So we're going to use /28 because we had 24 bits in the network portion plus the 4 bits we used for subnetting. Okay, so subnet number 1 went from 10.10.10.0, and with /28, it means that the broadcast IP for this subnet was 10.10.10.15, because when you take the host portion, which was 4 bits, and fill that with 4 ones, that's 15. Let's have a binary format down here to make it easier. So this is what the first subnet network ID is, 10.10.10.0. The second subnet network ID is going to be the next address after the broadcast address from the first subnet, which is 10.10.10.16. And let's look at what that looks like in the binary format. So we just changed the last bit in the subnetting portion. The broadcast address in the second subnet is going to be 16, so this one, plus 15, because we would get 15 if we switched these 4 zeros into 4 ones. So that's 10.10.10.31. Third subnet is going to go from 32 to 47, And then fourth subnet is going to go from 48 to 63. And then fifth subnet is from 64 to 79. And we can already see that the answer to our question is no. But let's look at the sixth subnet, which goes from 80 to 95. Now we're sure that these two addresses are not in the same subnet. 10, 10, 10, 72 is somewhere in the fifth subnet, and 10, 10, 10, 80 is the network ID of the sixth subnet. Next question. Could you allocate the address 10, 10, 10, 96 to a router interface? A router interface is just like any other endpoint device within a network. So you can't give it a network ID or a broadcast IP address. You can allocate any other IP address within the subnet, but the network ID and broadcast IP address. So when we look at the sixth subnet, it goes from 10, 10, 10, 80 to 10, 10, 10, 95. You already know what that means. The network ID of our seventh subnet is going to be 96. So that's going to be a network IP address. So the answer to second question is no. You can't allocate that address to a router interface or any other device in a network. Question number 3. What's the first address you could allocate to a router or any host in that range? Of course, here we are talking about this subnet from a previous question. And as we saw in that table, this address 10.10.10.96 is a network ID. So the first usable IP address is 10.10.10.97. And that address can be allocated to a router interface or a computer or any other device on that network. So our answer here is 10.10.10.97 is the first usable IP address. Subnetting with variable length subnet masks, example number 1. A company uses address range 10.0.0.0/8 and they want to create smaller subnets, and these are their requirements. They want 2 500 hosts subnets, 1 subnet with 220 hosts, 4 50 hosts subnets, 3 subnets with 10 hosts per subnet, and then finally 2 point-to-point subnets. We're going to start off with a table, and first we're going to fill in the number of hosts required for each subnet. We're going to sort those subnets from the largest one to the smallest one. And a small disclaimer here. In each of these subnets, we're actually going to need 2 more IP addresses than is stated here. So for example, in the requirement, we're told that the first subnet is going to have 500 hosts. So we need 500 IP addresses, but then we need 2 additional IP addresses, 1 for network ID and 1 for broadcast IP address. We're going to consider this in our next example, but for now, we're going to use the exact number of hosts as the number of IP addresses that we need for each subnet, except of course for the last 2 networks, because it's really obvious that we need at least 4 IP addresses in a point-to-point network. Okay, so the first subnet is going to have a 10.0.0.0 network ID, because that's what we got in the requirement, and so that's what we're starting with. This is what 10.0.0.0 looks like in the binary format, and I've underlined the first octet because that is our default network portion. We're going to use 9 bits for our host portion because that gives us 512 different combinations. If we used 8 bits, 2 to the power of 8 is 256, and that's not enough for our requirement for our first subnet. So we're going to go with 9 bits. That means our new mask is /23. 23 plus 9 equals 32, which is a total number of bits in an IPv4 address. That's how we got that number. Now let's think about the broadcast IP address. To determine the broadcast address, we need to switch all of the bits from our host portion into ones. So when we do that, we have 9 ones at the end of our IP address. So the broadcast IP is going to be 10.0. Those are the 2 first octets, and they haven't changed. But the 3rd octet has changed, and that's going to be 1. And then the 4th octet is going to be 255. So the broadcast IP is 10.0.1.255. Now the range is the easiest one to determine because we're just going to go from the first address after the network ID and then up to the one address before the broadcast IP address. So we're going to go from 10.0.0.1 to 10.0.1.254. Our next subnet's network ID is just going to be the next address after the broadcast IP from the first subnet, which is 10.0.2.0. And this is what it looks like in binary format. Now we're going to use /23 mask here too, because we also need 500 hosts for this subnet. And then for the broadcast IP, we're going to switch the host bits to ones, which means that the 3rd octet is now going to be 3, and the 4th octet is going to be 255. So the broadcast IP is 10.0.3.255. Range of usable addresses goes from 10.0.2.1 to 10.0.3.254. Network ID for the 3rd subnet is obviously going to be 10.0.4.0, and this is what that looks like in binary format. This time we're going to use 8 bits for the host portion because 2 to the power of 8 is 256, and that's enough to fit the 220 hosts from our requirement. 32 minus 8 is 24, so that's our new mask, /24. And we're going to switch the 8 host bits into ones in order to get our broadcast IP address. So since the first 3 octets haven't changed, that's going to be 10.0.4.255. Range is easy. It's going to go from 10.0.4.1 to 10.0.4.254. And then our 4th subnet's network ID is going to be 10.0.50, which is the next address right after the broadcast IP of our 3rd subnet. Let's see what that looks like in binary format. So this is 10.0.50 in binary format. This time we're going to use 6 bits for our host portion because 2 to the power of 6 is 64. So we can fit the 50 hosts into that. So that's good enough for us. If we use 6 bits for hosts, that means our new mask is going to be /26. So we have 26 network bits and 6 host bits. To get a broadcast IP, we're going to switch all of the host bits into ones. And now the value of this 4th octet is going to be 63. So our broadcast is 10.0.5.63. Range is as always easy. It goes from 10.0.5.1 to 10.0.5.62 in this example. Next subnet's network ID is 10.0.5.64, and this is what that looks like in binary format. The mask obviously remains the same, and then to get the broadcast IP, instead of 6 consecutive ones, now we have 7 consecutive ones. So these 6 consecutive ones added up to 63, and then 63 plus 64, which is the value of this bit, equals 127. So that's our broadcast IP, 10.05.127. Range is again easy. It goes from 10.05.65 to 10.05.126. Again, our next subnet network ID is going to be the address that comes right after the broadcast IP from our previous subnet, which is in this case 10.05.128, and this is what that looks like in binary format. Mask, of course, remains the same, /26, and then for the broadcast IP, we're going to switch all the host bits into ones. These 6 ones add up to 63, and this first one is 128, so 128 plus 63 equals 191. So our broadcast IP is 10.05.191. Range of usable IP addresses go from 10.05.129 to 10.05.190. And then one more of these 50 hosts networks. Network ID is going to be 10.05.192. Mask remains the same, /26. And this is what this looks like in binary format. Broadcast IP is this time easy to calculate, is going to be 10.05.255 because we've finally filled up the 4th octet with ones. Usable IP addresses range from 10.05.193 to 10.05.254. Next subnet network ID is 10.060. Let's see what that looks like in binary format. So right now we have 5. In order to get 6, we're going to switch these 2 bits. Now we need to determine the mask. We're going to use 4 bits because 2 to the power of 4 is 16, and we only need 10 addresses, so 16 will do. This means that our new mask is /28. Now, I want to stop for a minute here and explain something further. Up until now, we've used this CIDR format for our masks, but you should know that you can't always use this format. For example, when you're configuring a router, you can't just say, here's your IP address, for example, 10.065, and then say /28 or 26 or whatever. You can't. You have to write a mask in a decimal format. So for /28, you have 28 ones and then 4 zeros. This is how masks work. In decimal format, that's 255 in the first 3 octets, and then in the last octet, we have 240. So that's what you would type in to a router if you're using a /28 mask. All right, let's move on. So to determine the broadcast IP, we need to switch the last 4 bits into ones. That's going to be 15. So the broadcast is 10.06.15, and the range goes from 1 to 14. Network ID of the next subnet is going to be 10.06.16, and this is what that's going to be in binary format. Broadcast for this subnet is going to be 31, so 10.06.31. Range goes from 17 to 30, and then the network ID for our next subnet is going to be 10.06.32. Mask stays the same, /28, and this is what that looks like in binary format. Now, broadcast is going to be 32 plus 15, which is 47. So it's 10.06.47, and then range goes from 32 to 46. Again, network ID for our next subnet is just the next IP address, and in this case, that's 10.06.48. And this is what that looks like in binary format. The mask, of course, is going to be /30 as we've discussed earlier. And then broadcast is going to be 48 plus 3, which is 51. So that's 10, 0, 6, 51. As for the range, we can anyway only use 2 IP addresses, and these 49 and 50. Finally, our last subnet network ID is 10.0.6.52, and this is what that looks like in binary format. The mask, of course, remains the same, /30. For the broadcast IP, we need to switch these last 2 bits into ones. When we do that, we get 55, so our broadcast IP is 10.0.6.55. As for the range of usable IP addresses, again, we can only use 2, and in this case, those 2 are 10.0.6.53 and 10.0.6.54. Subnetting with VLSM, example number 2. This time, we have a company that uses a public range 176.33.202.0/23. They want to create smaller subnets, and these are their requirements. 2 point-to-point subnets, 1 subnet with 100 hosts, 3 subnets where each subnet has 4 hosts, and then 2 subnets where each subnet has 13 hosts. Again, we're going to start with a table, and we're going to sort the subnets from the largest one to the smallest one. This time, I've counted in the network ID and the broadcast IP address. So instead of just copying the requirement that said we need, for example, for the first subnet, 100 hosts, I'm saying here we actually need 102 IP addresses, and same goes for all the other subnets. All right, let's dig in. So the first network ID for the first subnet is going to be 176.33.202.0. And this is what that looks like in binary format. So in the very beginning, in the requirement, we got /23 mask. So this is 23 bits that represent the network portion. And those are the underlined bits in this representation right here. Next thing we need to determine is how many host bits we're going to use to be able to create 102 different combinations. We'll go with 7 bits because 2 to the power of 7 is 128. And that is good enough for us because we need only 102. So our new mask is going to be /25. We got that from 32 minus 7. That's exactly 25. So that's the 25 network bits in our new subnet. To calculate the broadcast IP, we're going to switch these 7 host bits into 7 ones. In total, the 4th octet is 127, and since the first 3 octets haven't changed, our broadcast is 176.33.202.127. Range of usable IP addresses goes from 1 to 126, and the network ID of our second subnet is going to be 176.33.202.128. And this is what that looks like in binary format. So only the first bit is switched on. This first bit has a value of 128. We're going to go ahead and use 4 host bits, which means that our mask is going to be /28. 2 to the power of 4 is 16. So we are a bit tight here, but it does meet our requirements for the second and third subnet, so we're going to go ahead with 4 bits. To calculate the broadcast IP, we're going to switch the last 4 bits into 4 ones. In total, that's going to be 15 plus 128, which is 143. So the broadcast IP is 176.33.202.143. And then the range goes from 129 to 142. Our next network ID is 176.33.202.144, and the mask remains the same. This is what that looks like in binary format. And then when we switch the host bits into ones, we get the broadcast IP 176.33.202.159. Range of usable IP addresses goes from 145 to 158. Next subnet network ID is 176.33.202.160. This is what that looks like in binary format, and this time we're going to use 3 host bits. 2 to the power of 3 is 8, and that satisfies our requirements for our next 3 subnets. When we switch the last 3 bits into ones, we're going to get 167 in our last octet, so that's our broadcast IP. And then the range goes from 161 to 166. Now we're going to go a bit faster for the next 2 subnets. So first of all, the mask remains the same. It's going to be /29. And then the network ID for our 5th subnet is going to be 168. Now this is pure math. So if we can only create 8 different IP addresses in our 4th subnet, that means we can just add 8 to that network ID and get the next network ID. That's what we're going to do for our 6th subnet. So 168 plus 8 is 176. So those are the network IDs. The 6th subnet is also going to have a total of 8 IP addresses. So the next network ID for our next subnet is again going to be that network ID plus 8, which in this case is 184. Now we can cheat a little bit with the broadcast IPs. So the broadcast IP for this subnet, let me see, that's the 5th subnet. So the broadcast IP for this subnet is going to be 175 because that's network ID of the next subnet minus 1. And then the next broadcast IP is going to be 183. The ranges we don't really care about anymore. Hopefully you got how we determine the ranges of usable IP addresses. The last 2 networks are point-to-point networks. So that's even easier. We can go one by one. So network ID is 184, and then the range of usable addresses is 185 to 186. And then the broadcast IP is the next address, 187. Last but not least, network ID is going to be 176.33.202.188. The 2 usable addresses are going to be 189 and 190. And then the broadcast IP is going to be 191. In this example, our task is to create a summary IP address. As I explained in one of the previous lessons, it makes sense to create a summary IP address when you have a lot of consecutive subnets. In this scenario here, we have 3 networks called areas. So maybe you're familiar with this terminology. If not, doesn't matter. So these are just 3 different networks. And it takes just a couple seconds to look at this scheme right here and notice that all of these subnets in area 0 are consecutive. So it's 96, 97, 98, 99, 100, 101, and 102. So in order to create one summary IP that is going to represent all of these networks, we're going to list all of them in one table. The first network is 96, and this is its binary representation. To make things easier, I put these binary values up here. So 96 is going to be 64 plus 32. So this is the binary value of the first network. The second network, 97, is going to be similar. The only difference is in the last bit. And the third network, 98, is also going to be similar, but the last 2 bits are going to switch. And then I'm just going to list the rest of them right away. Now the only thing left to determine is up until which point are these subnets the same, or up until which bit. So how many bits are the same for all of these subnets? We can determine that by looking at these numbers. So only the 3 bits in this third octet are different. All the way up to this point, all of these subnets match. So I'm just going to draw a line right here, and this line is actually going to be our new mask. We're going to copy all of the bits that match, so all of the bits from the first bit until the 21st bit, and this is going to be the 21st bit because we are in our third octet here. So this is bit number 21, this is 22, this is 23, and this is 24. So all of the bits left to the red line, we're going to copy, and then all of the bits right to the red line are going to become 0. And that's actually it. We already have our summary IP. It's 192.168.96.0/21. There is one more thing I want to mention here. So there's one more IP address that isn't listed here, but it does fit into this summary IP, and that's 192.168.103.0. So you should be careful when doing this, and I'm going to show you why right now. Let me go back to the first slide. Okay, so let's imagine that this Area 2 network has a couple more routers in it, and that one of the subnets is this 192.168.103/24 network. If router 6 is configured with this summary IP, it's going to think that all of those subnets from 96 to 103 are to its left, or that they are connected to this interface right here. And if that's not the case, if this 103 subnet is somewhere to the right, then you're going to have a routing problem. But regardless, you're still going to be asked to summarize networks, and this scenario is just one of the risks that you're going to decide whether you're going to take it or not.